Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12 physics, magnetism and matter. Chapter 5 NCERT solution part 4. Our mission is to provide free classes on YouTube for all students of class 6 to class 12, special classes for the students preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we start today's session, we have a small request to subscribe, like, and share our YouTube channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's class. So today we'll start with question number 5.18. A long straight horizontal cable carries a current of 2.5 ampere in the direction 10 degrees south to west to 10 degrees north to east. The magnetic meridian of the place uh, happens to be 10 degrees west of the geographic meridian. The Earth's magnetic field at the location is 0.33 G. The angle of dip is 0. Locate the line of natural points. Ignore the thickness of the cable. Let us see the solution. (5.18) Current in the wire I is equal to 2.5 ampere. Angle of dip at the given location on Earth, delta is equal to 0 degree. Earth's magnetic field H is equal to 0.33, G is equal to 0.33 multiplied by 10 to the power minus 4 Tesla. The horizontal component of the Earth's magnetic field is given as H is equal to H cos delta. Putting the value of H and delta, we get 0.33 multiplied by 10 to the power minus 4 cos 0 degree, which is equal to 0.33 multiplied by 10 to the power 4 minus 4 Tesla. The magnetic field at the neutral point at a distance r from the cable is given by the relation H is equal to mu naught I upon 4 pi r, where mu naught is the permeability of free space. Its value is 4 pi multiplied by 10 to the power minus 7 T m a inverse. R is equal to mu naught I upon 2 pi h. Putting the value of mu naught I, pi and h, we get 4 pi multiplied by 10 to the power minus 7 multiplied by 2.5 upon 2 pi multiplied by 0.33 multiplied by 10 to the power minus 4 is equal to 15.15 multiplied by 10 to the power minus 3 meter, which is equal to 1.51 centimeter. Hence, a set of neutral points parallel to and above the cable are located at a normal distance of 1.51 centimeter. Let us see the next problem. Next question is 5.19. One telephone cable at a place has 4 long straight horizontal wires carrying a current of 1.0 ampere in the same direction east to west. The Earth's magnetic field at the place is 0.39 G and the angle of the dip is 35 degree. The magnetic declination is nearly zero. What is the resultant magnetic field at 0.4 centimeter below the cable? Let us see the solution. So the solution for problem number 5.19 is The number of horizontal wires in telephone cable N is equal to 4. Current in each wire I is equal to 1.0 ampere. Earth's magnetic field at a location H is equal to 0.39 G, that is 0.39 10 to the power minus 4 T. Angle of deep at location delta is equal to 35 degree. Angle of declination theta is equal to 0 degree. For a point 4 centimeter below the cable, distance r is equal to 4 centimeter, that is 0.04 meter. The horizontal component of Earth's magnetic field can be written as HH is equal to H cos theta minus B, where B is equal to magnetic field at 4 centimeter due to current I in the 4 wires, that is 4 into mu naught I upon 2 pi r, where mu naught is equal to permittivity of free space, that is equal to 4 pi multiplied by 10 to the power minus 7 TMA inverse. Therefore, B is equal to 4 multiplied by 4 pi multiplied by 10 to the power minus 7 multiplied by 1 upon 2 pi multiplied by 0.04. Upon solving, we get zero point 0.2 multiplied by 10 to the power minus 4 Tesla, which is equal to 0.2 G. HH is equal to 0.39 cos 35 minus 2, 0.2 minus 0.2. Putting upon solving, we get 0.39 multiplied by 0.819 minus 0.2, which is approximately equal to 0.12 G. Vertical component of Earth's magnetic field is given as H vertical, HV is equal to H sine delta. So putting the value of H and delta, we get 0.39 sine 35 degree is equal to 0.22 G. The angle made by the field with the horizontal component is given as theta is equal to tan inverse H vertical upon H horizontal, which is equal to tan inverse 0.22 upon 0.12, which is equal to 61.39 degree. The resultant field at the point is given as H I is equal to under root HV square plus HH square. Putting the value of HV and HH, we get under root 0.22 square plus 0.12 square. Upon solving, we get for a point 4 centimeter above the cable, horizontal component of Earth's magnetic field HH is equal to H cos delta plus B, which is equal to 0.39 cos 35 plus 0.2, which is equal to 0.52 G. Vertical component of Earth's magnetic field, that is HV is equal to H sine delta, that is 0.39 sine 35 degree, that is 0.22 G. Therefore, angle theta is equal to tan inverse H vertical upon H horizontal. Putting the values of H vertical and H horizontal, we get tan inverse 0.22 upon 0.52, which is equal to 22.9 degree. And resultant field H Z is equal to under root HV square plus HH square. Putting the value of HV and HH, we get point under root 0.22 whole square plus 0.52 whole square. Upon solving, we get 0.56 Tesla. Let us move to the next question. So next question is 20.5.20. A compass needle free to turn in horizontal plane is placed at center of circular coil 30 turns and radius 12 cm. The coil is in the vertical plane making an angle 45 degree with the magnetic meridian. When the current in the coil is 0.35 ampere, the needle points west to east. A. Determine the horizontal component of Earth's magnetic field at the location. B. The current in the coil is reversed and the coil is rotated about the vertical axis by the angle of 90 degree in the anticlockwise sense looking from above. Predict the direction of the needle. Take the magnetic declination at the place to be 0. Now let us see the solution. So solution to 5.20 is number of turns in the circular coil n is equal to 30, radius of the circular coil r is equal to 12 centimeter, that is 0.12 meter, current of the coil I is equal to 0.35 ampere, angle of T delta is equal to 45 degree, A is equal to magnetic field due to the current I at distance r is given as B is equal to mu naught 2 pi Ni upon 4 pi R, where mu naught is equal to permeability of free space, that is 4 pi multiplied by I d about 4 pi multiplied by 10. Putting the values, we get B is equal to 4 pi multiplied by 10 to the power minus 7 multiplied by 2 pi multiplied by 30 multiplied by 0.35 upon 4 pi multiplied by 0.12. Upon solving, we get 5.49 multiplied by 10 to the power minus 5t. The compass needle points from west to east. Hence, the horizontal component of Earth's magnetic field is given as BH is equal to B sine T delta, which is equal to 5.49 multiplied by 10 to the power minus 5 sine 45 degree, which is equal to 3.88 multiplied by 10 to the power minus 5 t, which is equal to 0.388 g. Let us see the next problem. Let us see the next part of this problem. B. When the current in the coil is reversed and the coil is rotated about its vertical axis by an angle of 90 degree, the needle will reverse its original direction. In this case, the needle will point from east to west. Let us see the next problem. Next problem is 5.21. A magnetic dipole is under the influence of two magnetic fields. The angle between the field direction is 60 degree and one of the field has a magnitude of 1.2 multiplied by 10 to the minus 2 Tesla. If the dipole comes to a stable equilibrium at an angle of 15 degree with the field, what is the magnitude of the other field? Let us see the solution. So the solution is magnitude of one of the magnetic field B1 is equal to 1.2 10 to the power minus 2 Tesla. Magnitude of other magnetic field is equal to B2. Angle between the two fields theta is equal to 60 degree. And stable equilibrium. At stable equilibrium, the angle between the dipole and the field B1 is equal to theta 1. Theta 1 is equal to 15 degree. Angle between the dipole and the field B2 is equal to theta 2 is equal to theta minus theta 1, that is 60 degree minus 15 degree, that is 45 degree. At rotational equilibrium, the torques between both the fields must balance each other. Torque due to the field B1 torque due to the is equal to torque due to the field B2. So the value for the torque due to field B1 is m B1 sin theta 1 is equal to the value of torque due to field B2 is equal to m B2 sine theta 2, where m is equal to magnetic moment of the dipole, B2 is equal to B1 sine theta 1 upon sine theta 2. Putting the value of B1 theta 1 theta 2, we get 1.2 multiplied by 10 to the power minus 2 multiplied by sine 15 upon sine 45 degree. Upon solving, we get 4.39 multiplied by 10 to the power minus 3. Hence, magnitude of the other magnetic fields is 4.39 multiplied by 10 to the power minus 3 T. Let us see the next problem. 5.22. Next question is 5.22. A monoenergetic 18 keV, that is kilo electron volt, electron beam initially in the horizontal direction is subjected to the horizontal magnetic field of 0.04 G normal to the initial direction. Estimate the up and down deflection of the beam over the distance of 30 centimeter. ME is equal to 9.11 multiplied by 10 to the power minus 19 C. Let us see the solution. So energy, the solution for 5.22. Energy of electron beam E is equal to 18 kilo electron volt, that is 18 into 10 to the power 3 electron volt. Charge on the electron E is equal to 1.6 into 10 to the power minus 19 coulomb. E is equal to 18 into 10 to the power 3 multiplied by 1.6 multiplied by 10 to the power minus 19 joule. Magnetic field B is equal to 0.04 G. Mass of an electron Me is equal to 9.11 10 to the power minus 19 kg. Distance up to which the electron beam travels D is equal to 30 centimeter is equal to 0.3 meter. We can write the kinetic energy of the electron beam as E is equal to half mv square. So V is equal to under root 2E by m is equal to under root 2 multiplied by 18 multiplied by 10 to the power 3 multiplied by 1.6 multiplied by 10 to the power 19 minus 19 multiplied by 10 to the power minus 15 upon 9.11 multiplied by 10 to the power minus 31 is equal to 0.795 multiplied by 10 to the power 8 meter per seconds. So electron beam deflects along a circular path of radius r. The force due to the magnetic field balances the centripetal force of the path. That is, BEV is equal to mv square by r. R is equal to mv upon BE. Putting the values, we get 9.11 multiplied by 10 to the power minus 31, 0.795 multiplied by 10 to the power 8 upon 0.4 multiplied by 10 to the power minus 4 multiplied by 1.6 multiplied by 10 to the power minus 19 is equal to 11.3 meter. Let the up and down deflection of the electron beam be x is equal to r multiplied by 1 minus cos theta, where theta is the angle of declination. Sin theta is equal to d by r. Putting the value of d and r, we get 0.3 upon 11.3. So theta is equal to sin inverse 0.3 upon 11.3. Upon solving, we get theta is equal to 1.521 degree and x is equal to 11.3 bracket 1 minus cos 1.521 degree. Upon solving, we get 0.0039 meter. which is equal to 0.39 millimeter. Therefore, up and down deflection of the beam is 0.39 millimeter. Let us see the next problem. Now we'll see problem number 5.23. A sample of paramagnetic salt contains 2 into 10 to the power 24 atomic dipole. Each dipole moment 1.5 multiplied by 10 to the minus 23 joule per Tesla. The sample is placed under homogeneous magnetic field of 0.64 Tesla. The cooled to a temperature of 4.2 K. The degree of magnetic saturation achieved in is equal to 15%. What is the total dipole moment of the sample for a magnetic field of 0.98 Tesla and a temperature of 0.28 K? Let us see the solution. So 5.23 solution is number of atomic dipoles n is equal to 2.0 into 10 to the power 24. Dipole moment of each atomic dipole capital M is equal to 1.5 into 10 to the minus 23 joule per Tesla. When the magnetic field B1 is equal to 0.64 Tesla, the sample is cooled to a temperature T1 is equal to 4.2 degree Kelvin. Total dipole moment of atomic dipole M total is equal to N into M. Putting the value of N and M, we get 2 into 10 to the power 24 multiplied by 1.5 multiplied by 10 to the power minus 23. Upon solving, we get 30 joule per Tesla. Magnetic saturation is achieved at 15%. Hence, effective dipole moment M1 is equal to 15 upon 100 multiplied by 30, that is 4.5 joule per Tesla. When magnetic field B2 is equal to 0.98 Tesla, temperature T2 is equal to 2.8 K, the total dipole moment M2 is equal to M2. According to Curie's law, we have a ratio of two magnetic dipole as M2 upon M1 is equal to B2 upon B1 multiplied by T1 upon T2. Therefore, M2 is equal to B2 T1 M1 upon B1 upon T2. Putting the values of B2, T1, M1, B2, B1 and T2, we get 0.98 multiplied by 4.2 multiplied by 4.5 upon 2.8 multiplied by 0.64. Upon solving, we get 10.336 joule per Tesla. Therefore, Therefore, 10.336 joule per Tesla is the total dipole moment of the sample for a magnetic field of 0.98 Tesla and a temperature of 2.8 K. Let us see the next problem. So the next question is 5.24. A Roland ring of mean radius 15 centimeter has 3500 turns of wire wound of ferromagnetic core of relative permeability 800. What is the magnetic field B in the core for the magnetizing current of 1.2 ampere? So the solution of 5.24. The mean radius of Roland ring R is equal to 15 centimeter, which is equal to 0.15 meter. Number of turns of ferromagnetic core N is equal to 3500. Relative permeability of the core material mu R is equal to 800. Magnetizing current I is equal to 1.2 ampere. Magnetic field is given by the relation A is equal to mu R mu naught I N upon 2 pi R, where mu naught is equal to permeability of free space 4 pi, whose value is 4 pi multiplied by 10 to the power minus 7 TMA inverse. Putting the values, we get B is equal to 800 multiplied by 4 pi multiplied by 10 to the power minus 7 multiplied by 1.2 multiplied by 3500 upon 2 pi multiplied by 0.15 is equal to 4.48 Tesla. Therefore, the magnetic field in the core is 4.4 Tesla. So here some corrections is there. So here by mistake A was written, it is B, magnetic field. So let us see the next question. So the next question is 5.25. The magnetic moment vectors mu s and mu l associated with the intrinsic spin angular momentum s and orbital angular momentum l respectively of an electron are predicted by quantum theory to be given by mu s is equal to minus e by m s, mu l is equal to minus e by 2m l. Which of these relation is in accordance to the result accepted classically? Outline the derivation of the classical results. So let us see the solution. The magnetic moment associated with the intrinsic spin angular momentum and the orbital angular momentum. And this is the end of the chapter. Before we close today's session, we request you to subscribe, like and share our YouTube channel. Please click on the subscribe button to support us, and please click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for watching our videos in Experienced Tutor and supporting us. Thank you very much.